So again, I'm Ari. Just get a feel for the room. Has anyone ever used DL4J or the Skymind stack? All right, cool. All right, so rather than kind of giving you an intro to just a general stack, I focus on some of the other aspects of it. Primarily people come in from other areas, meaning you come from Keras or when you're starting out just a general prototype project and how you scale that. So I'm going to focus a lot on ingestion and modeling and then scaling your network. And then I have an LSTM network that I can kind of walk through, kind of putting all the pieces together and go through that. And then I have some resources for you. So this is really what I hope you take away and scale from the initial research to production. But when a lot of people start out with DL4J, they're not really sure like how all the components map together. So I hope you get an idea of what these different pieces are. I'm moving up to the front.
I don't hear you.
Okay. Can everyone hear me? Fine? All right, cool. So if you're not familiar with Skymind, we focus only on the production side, which is why we don't have any Python binding. So our complete stack is in Java and Scala. So we're just in a different user base completely. And that's why I like all our customers on that side. We don't really work with startups that much. They're typically more in the big enterprises. We had developed the complete stack from scratch, so we actually don't have a lot of other open source ones other than maybe like Java OpenCV. We have a lot of different segments that we work in, government, finance, retail, telecom. Recently started doing a lot more in robotics with SoftBank. If you're familiar with them, they're the ones that acquired ARM last year. So. And there are a lot of different use cases. One that's not in here is probably more on the tech side, more like part manufacturing. So like Boeing is one too that we work on a lot right now. But computer vision, just like you see with a lot of deep learning frameworks too, we do a lot there as well. So this is why we do everything in Java. Partly it goes back to our co-founder, Adam. This pretty much had started this all in Java, so it's been around since 2013. And then 2014, the stack was born, and so the stack is deep learning 4J, and then there was DL4J, and that's really not just like the modeling stack, it's a complete suite. So that will focus everything you need to do from how you ingest your data, how you model, and how you distribute it. So 9.1 is our latest release. And that was just in August, but we're doing a lot right now, and we've been recently accepted into the Eclipse Foundation, so we're working on our first release for that. And so right now I'm actually pulling a lot of stuff from our master branch. Snapshots are currently not working for us, so I'm just pulling everything from master right now. So, and you'll see that there's a lot of different new features that I'll be talking about as well. That's on the master branch and not in the 9.1. And you can see that 9.1 was just very recent. So I'll blow this up for you. So it's kind of like what our stack looks like. At the very top, ScalNet is kind of like the equivalent of Keras, but it's a really lightweight one, and we typically just use it for the modeling side. Everything else kind of comes out of the main DL4J side. And so that's the suite from the modeling of it. Below that is the Datavac, which we call our ETL side of it. And then ND4J, which is kind of like NumPy for JVM. There's ND4S, yeah.
Are you also supporting ND4S? Is it also your part of the product?
Say again?
ND4
yeah.
Is your product?
Yeah, it is.
Are there any plans to support native like Scala map functions and so on? Because there is still
Yeah, that one actually you can do directly from Scala, right? So if you want to use the Scala map function itself, just like in Java, right? It's just that it's kind of like a wrapper around it. So ND4J, you'll use that all for Java. But if you want to do stuff in Scala, then you can use ND4S directly.
Okay, because the last time I saw it, there was like open issue with like,
yeah. Yeah, that's what I mean. There's been a lot of changes recently this year. So if you like pull from master instead of the latest release, then you'll get that. And there will be another release coming up soon. I'm not sure when because of the whole Eclipse Foundation that we're moving towards. That's why I'm pulling stuff from master. And jumpy is kind of like now you can do stuff around a Python interface to it. So it's a way just like you would create a NumPy array and do it. So that's part of what we're doing in the migration towards right now for Keras. We have a Keras model import, but we're not currently a backend to Keras yet. So that's in the roadmap. So then that's all in the Java side. And then below that, now we move down to native. And the native side, that's where all the Java CPP, the libnd4j, the hardware architecture, and the chip libraries come in. And all that kind of comprises what we call backends, right? So even the Java CPP, when we cross from the Java world to the C++ world, right, we don't actually go through the JNI. It's all like hand manipulated, just parsed. So it's almost like function pointers. So we don't have to pay the overhead in that. And we actually do a lot of this off heap. So all the ND4J stuff is all off heap. So we don't have to deal with the garbage collection. And there's been advances in with workspaces. So you could essentially attach a memory to a particular workspace, whether you got a beefy machine or not. And then you can detach it when you don't need it. So you don't have to pay the penalties for that. Yeah. Yeah. Do you not hear?
It's
very light. Yeah. Okay, yeah, I guess everyone can hear me now better now. So when we go over to the hardware architecture side of it now, so we pick up on GPU or CPU. And I'll talk about this later, but you could switch out which one that is. And by default, like the accelerator libraries, when you get out from Maven and just pull those out, you get the OpenBlast. But if you want the Intel MKL, then you can integrate that into the hardware architecture on the back end. All right, so it just kind of depends what you want to include, and it's just a switch for a GPU versus a CPU.
Quick question, so does it mean that you switch it at the artifact level?
Yeah, that one you actually switch at the POM level, or you could switch by environment variables. So so it's basically you go into a project object module, just go ahead and switch your dependency. As long as we see it and you're on a machine that has it, we'll always go to the GPU. So these are the different use cases we got coming in, different types of data. So kind of like your TAL, your sample data for fits in memory. And then we got the next level, which where you do your batch generators. So not going to fit in memory, but you can still batch it in. The next one where you do a little bit more custom based side, because we have these kind of built-in ones, and those are fine when you just put everything on your file system, but you want to move beyond that, and you can do your own custom generators for that too. So we give you a lot of things for depending on the type of data that you work with, as well as what type of volume of data you work with, and that's where you kind of fit with these three use cases, as well as what happens when you got imbalanced classes. And so we actually take care of that for you out of the box. So let me throw this one up. So this is part of our Datavac side. Datavac is our whole ETL. So we think about when you go ahead, instead of just like ingesting all in memory and all the NumPy arrays, you just basically ingest the location URIs, just the metadata essentially. And then as part of the metadata, when we get down through the vectorization ingestion, then we'll actually go bring these in at a batch at a time. So you're not actually bringing it in at that time of it. So when you actually do your transformations, when you do your pre-processing and then transformations, we could be smarter such those transformations happen at the batch level. You don't have to pre-process it and save that off. And that's where you make these trade-offs. And basically we have these, there's a couple different levels. There's like a record reader, and that's the vectorization side of it. From that the record reader, basically, like imagine you have the image data, you have text data, you have sequence data. We have all these different record readers for you. And then from that, you basically have these data set iterators, and that's how we batch those in based on your batch size. And that will pull in from the metadata. And from that, you could define transformations, just like in Spark, for example, you define your schema for it. Or if you want to augment it, like in Keras, for example, if you want to augment your image, for example, right, you could do that at the batch level and not have to pre-process it and then save that to disk. So here's like basic one. Okay, it's back. All right. So imagine you got some training data that you're loading in through just a CSV record. So this is like the simplest one. You bring in this record reader, you go ahead and define a file split of where it lives. It brings in that metadata, and now you go ahead and tell us about whether you're doing like regression or not, how many classes it has, and you would shuffle your data. Now, this is just like when all your data is in there. Essentially, you're doing everything what you would normally would have done, except you're just doing it on the like almost indexes instead of the actual data, because that's what the file split does. And then you would do your split test train, and then you would just do your normalization. But fortunately, it doesn't really happen when you start scaling with lots of data. So this is kind of like what you would start out when you're just kicking off a project. But when you want to kind of scale to the next one above that, you have two different other sides of it. So on the left-hand side, you still have the same idea of you load in, you would go ahead and resample it for equal weight distribution, and then you might do like a transform or execute. But you kind of get that back right away, right? And so instead of doing that and then shaping it on like your CPU and pre-processing it, I propose more on the right, where you go ahead and you load the metadata, you go ahead and do the balancing, and we have ones that would come in through like balanced path filters. But instead of actually doing the pre-processing and the transformations there, we do it on each batch. So that's where we basically just say, let's tell the iterator, in this case, these 32 sample batches that come in, and you basically, whenever you get the next iterator, you do the transformation at that point in time, and not earlier on. As well as, so, that's not what I want to do. Keep losing it. Is it back? And the last talk of the day. Okay, it's back. All right. That apparently does not seem to work well. Worse, all right. I'm gonna have to squint. I'll keep it that way. But the main takeaway for this is that what I'm doing here is you see that I'm basically defining a transformation process right up here. For example, if I go ahead and just bring in all my data, and I could set the schema for it, and I could go ahead and define a transformation process, and I take that transformation and put it in a dataset iterator, so I don't do that ahead of time. And now that this transformation dataset reader basically just wraps the iterator. So now you can be a little bit smarter on how you do with it. The other thing I'm doing at the bottom here is I'm actually doing an asynchronous dataset iterator. So you imagine that you have a couple ones, whatever your batch size is, you basically go in and get these asynchronously, and you can still continue to start to doing your training process. So you just go ahead and define your queue size for that. These are some of the built-in batch generators. So on the left side, you would see more like an image type example, where you would see, like, for example, test and train, and you would basically separate each folder with all your labeled images into that. And on the right-hand side, you'd probably see a little bit more what your sequential data would be. You would see like each one, in this case, these 1 through 10 are basically different engines, and within each of those CSV files are different temporal sequences. So in that way, you don't have to worry about all of this. You basically we have a sequence record reader, basically ingested it, and it'll take care of it, and it's just new batch data that comes in for you. You just need to define what that unique pattern is for you. So we have a numbered file one that comes out of the box for you, but you could just basically define any pattern you want and feed that in. All right, I'm going to try zooming in. Okay. All right, so this is part of that pipeline. On the left side, the orange one is more of the images. And this is what our typical workflow would have been. Figure out what your data source type, bring in label images, this parent path label generator we define, go ahead and initialize it, and then we go ahead and set our record reader, and then we'll define our normalization scaler. Notice that we don't actually do any normalization here. We just go ahead and tell the iterator based on what we collect the training fit data on. And then on the blue side is more of the sequential data, and that's probably what I'll focus on more here. And so now we have our numbered file split. We bring in through the record reader. We go ahead and do the transformation process we were talking about. And it's important that we collect the metadata for it, so when we actually do the predictions for it, we can actually correlate what that metadata, what it is for, whether what type of engine it was for or what type of image type it was. And now we go ahead and do the asynchronous dataset iterator, and this is basically your entire workflow up until you're ready to get training. So this is everything we do for Datavac. So here's some of the more custom-based ones. There's multiple different ways you could do it. And you can either think of it as, instead of actually loading in the data, we go back to loading indices, or in this case, you're loading it, instead of having that file structure that I showed you before, you basically just say, here are all the metadata. I get this from like a CSV, I get it from my own type of database, and you could just basically ingest this in. So, damn it. I lost you, didn't I? It came out. All right, I'm gonna not zoom in. So basically I'm giving it, doing a filter. I'm reading this in through Spark as a CSV file and ingest this in. I'm doing a filter on then, and I'm basically just converting the RDD down to a row and getting the URIs out of that. So you can think of just go ahead and reading all these in from a CSV file, so you don't have to have it in this custom directory structure at all. You just load in the actual structures.
Cannot you read it directly from data frame?
Yeah, so if you put that, in this case, I am reading this from a data set, close, a type data frame, right?
Yeah, but I see that you store it to file, right?
Yeah, so the thing with our side of it is, I'm reading this in from a CSV, a data frame, right? But when it comes down to it, right, we basically, when we put it down to our world side of it, it needs to come in through a list or an RDD, right? And at this point, before we're doing any of the data ingestion side of it, we need to go back from essentially the collection. So it goes from data frame, RDD, back to list. So we do the collection side of it, right? So the one thing is partially because of legacy, everything we do is at the RDD level. I'm just kind of showing this because of the more advanced stuff that we do now with data sets and data frames, but we've always been more native. So if you think of like even Big DL, they're more native to Spark, in contrast to some of the other ones where they lived at a higher level of serialization. So that's why all our interfaces are always going to be at the RDD level. All right. So this is another way you could do it with this collection input split. You could also just inherit from the dataset iterator and go and implement your own custom-based one. So now, once you kind of got more of the basics, basically I've just shown you more of you got a single output, you got a single input coming in, but you may want to go to more advanced-based ones with different metadata coming from different sources. So in this case, we got multi-data sets. And so you can either have multiple outputs or multiple inputs, right? So in this case here, I'm showing you with multiple outputs, where I'm showing like we have, as part of this, we have different features and labels coming from two different sources of files. And then towards the tail of that, we basically have two different outputs. Instead of just like a classification one, we can have one like classification, and then we can have another one like based on like images, and then we could do more of the temporal based nature of it. And this way we're still working with the whole dataset iterator, and it's just how we define it. So this is important for multitask, and as part of even on the input side of it, if you have one type of data, and now you can have almost two different types of networks coming in. And so it's just defining the type of dataset iterators as you get more enriched metadata for it. So that's kind of like the whole ingestion side of it, everything you would do up until training your network. And so now I'll go over to the modeling side. So there's a couple of different ways that you could do your models. The basic one is define your whole entire configuration from scratch. And then you would serialize that and reload it. The next side is the Keras model import. So instead of having people implement the entire configuration within DL4J, and doing everything in Java or Scala. They could do it in Python, and they could just import it in. Currently, we do stuff more like an MLP, just more of a basic level and an image level. The LSTM side of it currently does not allow us to return sequences that are not true. So we're always returning sequences. And when you go from a sequence to a dense layer, we currently don't support that. So we're currently in the works of working so we could do LSTMs on the Keras model import, but you could still do basic ones and image data for it. And the next one is we have our own model zoo. So just like you have all these other networks for it, we have some ones that are native to it. So I have a couple slides on those. So depending on what your use case is typically more popular with image type data, but you could just import that in and do transfer learning on that. So these are the different sides that I was talking about. So either you do initialization, Keras model import. Now as part of the model zoo, we have ways as part of a selector. So you could basically define of either you know the type of network that you want, or you know it's the type of use case. So in this case, you could say, okay, give me all the CNNs, or give me all the RNNs. Right now, there's like, basically all of them are CNNs, and there's one LSTM that we use for text. So those are the main ones we use. Now, we are working on, so far it's been like a Keras model import, but we're working on as part of our ingestion that you could start importing native-based ones, so the native backends. So the one that we're working on right now is native TensorFlow. So you can import those directly without going through Keras. So this, I would zoom in for you. Can anyone still see that? But basically this kind of shows the difference between DL4J and Keras if you're gonna implement this from scratch. And so there's two types of networks. We have like a multi-layer and we have a computation graph. Multi-layer is basically just a bunch of stacked sequential layers. And the computation graph gives you more control to basically do more advanced configurations. So you see like in Keras where basically we have this like input. And instead of basically just doing model adds, we basically just go ahead and just define what we want for the LSTM and this define what the input layer next would be. So we have that same way that we do here, and in this case it's just add layer. It's just a type of graph that we define. So in this case it's the computation graph. We actually define all our hyperparameters for tuning at the same level here. So computation graph configuration for it. And listeners are very similar to in Keras what you would do with callbacks, but they're a way for us to monitor our network. If you want to monitor, like for example, the score. But we have, just like you have, like for example, with TensorFlow, right? You have the tensor board. We also have our own monitor UI that we could monitor these. So ScalNet, like I said, it's a really simplistic one. It tries to model Keras. It only uses it for the modeling side of it. So it doesn't use it for the Datavac side of it, the evaluation side of it. It doesn't use it. It's a very lightweight one for just MLP-based ones or even convolution nets. So if you want to just kind of get started and you don't want to go through the whole Keras model import, right? You could do something like this. It follows, it's almost exactly alike to the Keras world. So it's just giving you another alternative if you just want to get something started quicker. So this kind of just gives you an idea of what Keras is today. Theano, TensorFlow, CNTK, and MXNet is in beta. And currently we don't support all out-of-the-box Keras functionality, but we support a good chunk of it. So like you could still do a lot of the basic ones that you got coming out. One of the ones that, for example, that we don't do right now is putting your own custom layer that you would get with Keras. But we have our own ways to define our own custom layers. So you could just do that natively in our own. But for the majority of that, besides like Lambda layers, we could do most of them. So this is the Keras model import. So you go ahead, if on the side you see on the left, that you go ahead and save it. You can either just save your entire network, or you can save your weights in your configuration file. And you could choose to go ahead and serve your network then. if you're not going to do further training on it. As part of that, Skele has always been in our enterprise world, and over the last month, we recently made a community-based edition. So you could actually do like a Zeppelin notebook directly in this, and you could do it like on AWS, or you could do it locally. It's currently run as part of CentOS, and that uses like a Zeppelin-based notebook if you want to use it for doing all your notebook-based stuff there, which traditionally has been difficult for at least the Scala and Java world. Or so if you're not going to go ahead and serve it and just go and do it for training on it, then you can do your import. Basically out of that, you'll get the type of graph, whether you're doing computational, which is more the functional API in Keras, or you're doing the sequential with the linear model. And so you can either just import, like I said, the entire H5 file, or you could split it up between the network configuration and the weight separately. And whether you wanted to enforce the train config or not is how we do the model serving or not. So basically it's a way for you to just, did you actually import it correctly or not, or if you just want to do inference. So here's the transfer learning, the model zoo. Couple of the frequently used models are the LeNet, the GoogleNet, the VGG world, the Inception, and recently the DarkNet and the TinyYellow for computer vision for object detection. So that's currently not in 9.1, but is in the master branch. And so if you want to do object detection, and so if you imagine before where you got the classification, and now you want to do your bounding boxes, and it's been difficult, at least not compared to Python world, to draw those around there, you could get that now with the TinyYellow. So transfer learning helper was originally started as part of our model zoo, and we actually had part of Keras, we had a whole trained models side of it, so that's kind of deprecated now, and we tend to use more transfer learning side of it. But transfer learning isn't really specific to the whole model zoo, or whether you're using it for just a convolution or net. So you could use it to import your model, and then from importing your model, you could then just freeze those layers and attach new layers to it as you continue to train. So in this way, we've defined a transfer model, a learning helper for you to easily do it. The right side shows that a way for you to basically, if you want to use initialized pre-trained weights, so in this case like ImageNet for a convolution neural net. There are trade-offs for that. I'll get into those, but you're not always going to be able to use that. So even if you import your model, but you're not conforming to the input dimensions, and you do not scale your data to those input dimensions, then you're basically falling back to the scratch model because you haven't tuned to that exact architecture. So this shows the learning helper, the phase one. So you go ahead and import your model. You get a copy of the model from it, depending on which type of model you have. Either you're doing an inference only, or you're going to fine tune it. And the fine tune, maybe you're changing the learning rate. You're basically looking at the architecture from what you imported in, and you're basically going to say how I want to change my current architecture. So my following layers that I'm going to train on it now, I want to change those. You could also override those in the individual layers themselves. And you could either, our dense layer is really an output layer. So you're basically going to set your feature extraction, and that would be freezing your earlier layers. And then you would basically drop out the output layer and put on our new output layer for it, keeping all the existing architecture. Or you're basically going to drop out the output layer and add new layers to it. So it takes one of two paths, depending if you want to freeze and then train additional layers from it, or if you just want to do inference and just change the output layer for it. So this follows it's a whole subway type map, if you're interested in that. So it's just easy for me to basically visualize it that way. With our evaluator is kind of like a metrics. So we have an earlier one, so it's just a basic evaluation, but we've brought ones in now for doing ROC, under the curve, confusion matrices, much like you would see in scikit-learn or Keras. So you basically define this evaluation class. And you could define a fresh one, just telling it the number of classes, for example, or you could get it from the existing dataset iterator. So as you import it in, you probably just want to go ahead and check that you got the same validation score that you got from like Keras or your Model Zoo. And then you want to move beyond that, and there's two ways to do your featurization with the freezing. On the right-hand side, you basically want to go through and featurize each of these data sets. And the data sets we get through each dataset iterator every time we call the .next. And then we want to go ahead and save those to disk. The left-hand side basically says, instead of saving those to disk, I'm just going to process it all at one time. So you could basically use an existing one, or you could go from scratch and train it all the way through. And the existing one will basically allow you for reuse for later on period of time. So you could save a bunch of data sets to it, and then you could pick that up at a later point in time and then do your evaluation. And then you would use the model serializer is how you would basically do your serialization to load in, to save, and then reload later on from disk. So we have a lot of things. They're just a little different mappings, but very equivalent to other frameworks. So this is part of the monitoring side I was talking about. Like TensorBoard, it defines a way for you to monitor your network, so you can see how it's training over time, or even how the validation happens. And so what you do before you do any of the fit stuff, you could either define it as an in-memory, or you could define it as a file. So when we go to Spark, you always either gotta do one of two things. You either gotta do like at a file-based level, not in memory, right, as it's going across different distributors, or you could define your monitor UI running on a different JVM than what it's currently training on. In that case, you would do like an enable remote listener and give it another IP address. But you could also just do it the file-based way too. And so that's what the left-hand side shows. And so you would basically go ahead and define this singleton instance. And in this case, I'm showing it in memory. And you could attach a bunch of different listeners to it. In this case, we defined one that was for the in-memory side of it. And then we could go ahead and look at the score listener for that, so you could see how it's training distributively. And then you would just go ahead and go to your training model and just go at like port 9000. That's the default port, which you could override. So I'm on time. All right, let's go through. So this kind of goes through the parallelization. So as we go through, start at the basic ones, the multi-layer and computation graph. Then we go up to parallel wrapper. This is a way to do single node if you only have one node you're doing it on, like one GPU, right? And then you could go up to the Spark layers. And we basically, these are just kind of wrappers around your existing architecture. So this is a single node one, and recently we added parallel inference as well, that you may actually want to do inference on a single node and not locally, instead of if you're doing like batch operations. And that was added in 9.0, I believe. So if you are, though, just doing a single node, even though you could use Spark for this, right, then you're going to do better by doing the parallelization with the parallel wrapper, even on the training side of it. So we recommend using that one. And this, it uses the existing network, and you basically just define how you want to distribute the workload. And it's very similar with the parallel inference. The multi-GPUs, this is the POM file I was talking about, where you could basically just change like this single line up here. Instead of native platform, you can just basically define the CUDA platform that you're coming in on, and then it'll automatically switch to the GPUs. An alternative would be, it always go ahead, as long as you're on a GPU and they have the native platform, it'll go directly to the GPUs, but you can override this to an OS environment variable as well, and the higher number will win. In contrast to TensorFlow, you could basically, instead of just saying what package you install, it's very similar to that, or doing device scoping. So we're very close to that. Another thing is floating precision. So you could scale down, instead of doing like F32, right? You may want to scale down and go to FP16, and it's literally just a single line for that. So this is a way for you to kind of save a lot on the memory side of it. And since I'm running short on time, I'm going to run through this. So this kind of shows you as you're scaling up that all your existing network architecture would stay the same. And what we're changing here is really just this parallel wrapper where you take the existing model for it. And now you're still going to do the fit on it. It's just that instead of fitting on the model, you're fitting on the parallel wrapper that it took as the input. The next one is a little bit more. This is the Apache Spark one where we basically define, take your existing configuration of the network, and then we define a parameter averaging. This one has been in there for our legacy. And we take a training master and decide how you want a parameter average across it. And the scaling out, this is new on 9.1, so Spark may be too much of an overhead for you. And so when in that case you're not using Spark, then we have Arion in there. It uses Akka underneath the hood for message passing, for low latency. And it's just a different type of training master. It's a void configuration, basically defining the type of port for you. But you see that everything, all your other entire workflow is exactly the same. Got it? So this is pretty much the last one. This kind of shows the difference between the parameter averaging and the shared gradients. And you can see that this is just a different type of training master. Originally, we started the training master with the idea that we could have many different ones. For the longest time, it was just parameter averaging that we used in Spark. And so recently, this was added in here where you basically just define the UDP port for unicast. And then you would go ahead and give that shared training master, give that as an input. The threshold defines that instead of actually saying, I'm not going to send it all at one time, you basically define some threshold where we'd store those to memory, so the next time those encoded thresholds go over. And I had an example to go through, but there's a network, but I think I'm kind of over on time. And I guess questions. Anybody have any questions about DL4J? Yeah.
Just a question. Do you think it would work on Cube?
Say again?
Do you know what is Cube? Cube?
Oh, yeah. Cube.
Will it work on Cube?
Don't know. I haven't tried that one.
So do you think you make like agreement? Because I asked Cube guys if they support deep learning for them. They told me like not especially.
Yeah.
And we are using Cube generally, so it would be like good if you could both make like agreement.
I'm guessing that it's going to require some customization to it, right? But I don't think it should be a heavy side of it, because we've had some customers come in and as part of it and not using Qubel, but still I think it's just an integration point. And this is what traditionally our skill has been at the skill level, where we did all these vendor integrations because people didn't have the Python bindings, right? That's where our skill level had done. And it hasn't been a huge effort in the past. So I can't talk about Qubel specifically because I don't know. Anybody else? Yeah, so I guess we're a little time, but basically in the GitHub kind of defines a workflow putting all the pieces together that I kind of showed you all the way up to the inference side. So it shows us like an ingestion coming in, and from the ingestion, then we'll take a regular network, and then from the regular network, then we'll go to a Spark one, and then from the Spark, you could basically show different monitoring side of it. And there's a Keras notebook in there too for you. So if you're interested or have any questions, feel free to reach out. But that was one that I was hoping to get to, but it's I guess a lot. And so feel free to reach out to me if you have any questions as well. And there's a couple examples. All our stuff is open source, pretty much, other than some small pieces on the enterprise for a skill. But it's all on GitHub, DeepLearning4J. And all our, even like the Datavac side of it, and D4J and D4S, it's all up there too. And we have a DL4J examples directory. And recently there's been a tutorials folder to DeepLearning4J added. And those have actually been exported notebooks that came, that we've exported them into IPython notebooks. So take a look at for our documentation side of it. And those are actually in Scala. So if nobody else has any questions, I guess go to the panel.
All right, thanks everyone.
All right.